This mini-lecture will focus on relativity theory and quantum theory. This week we're getting into physics, specifically modern physics, and our focus will be on the 19th and early 20th centuries, and bringing us up to the present, really, but the main configurations in quantum mechanics and relativity theory were taken care of in the first part of the 20th century, relatively early. Some of you may remember at the beginning of our class, we went around and each of us got to answer why we were interested in the interaction between religion and science. And I mentioned that that I'd always been interested in science and religion, and I felt that both of them tried to get to the ultimate nature of reality, the fundamental nature of reality, from different angles, but in their own way. They try to answer what's the ultimate nature or the fundamental nature of reality. And physics is probably the area that gets at that most basically, the basic elements, the basic material components, particles, forces, the elementary forces. As Barber mentions, physics does tend to get to the simplest, the lowest levels of organization, although actually it's a lot more complicated than that, as we'll see as we go along. To set the stage for talking about these later modern developments, we need to recall something and say a little more about the mechanistic view of things that prevailed during the Enlightenment, that Newton was the number one figure as far as establishing that. The Newtonian paradigm involved absolute space and time, and it involved Euclidean geometry. Nothing tricky, just space, 3 dimensions, absolute, continuous. We can measure it in whatever direction. Time, again, we can measure. It's a continuous flow from the past to the future. And both of those are absolute, separate in themselves. Neither affects the other. Everything gets localized then in space and time at any given moment. This is sometimes referred to as the billiard ball universe, right, where you kind of reduce things to fairly simple components. Here we do have kind of a reductionism to the simplest parts, and everything is assumed to be made up of these more or less uniform basic parts, and so at least if you know where everything is, just like supposedly if you know where a billiard ball is, and you know the force that's imparted to it, the friction of the velvet that it's on, you can know that it's going to bounce off there and then go there and just nick the 8-ball. The tendency was to say that everything is then deterministic, except many of these early thinkers would say that, well, human beings are the exception, our minds, we have free will, but at least in the purely physical dimensions of things are deterministic. They're basically predetermined by all the positions of everything in space and time, and the forces that then are enacted on these material objects. Olson in Ferngren talks about how this kind of Newtonian deterministic kind of world wasn't actually bought into fully by Newton himself, because he wanted to preserve, or thought we needed to preserve, some interventions by God to keep planets, including our Earth, from collapsing into itself because of gravity. He also felt the revolutions of planets around the sun needed to be adjusted by God periodically. All that was disproved. Laplace, with the nebular theory of the formation of the solar system that we referred to earlier in the course, showed that we didn't need special creation of our solar system. And so there was a tendency to push God out of the picture, or at least to the side, in this mechanistic view. Many of our founding fathers were deists who believed that God created the world initially, but then doesn't intervene, just lets things go according to the physical laws that Newton and others had discovered. We have minds. God allows us to learn and be taught through nature and learning from great minds what is morally right and morally wrong. So we don't need God to intervene, certainly not. And deism even tended to say, well, why does God even need to sustain it? Maybe God knows what's going on, maybe not, but we're kind of on our own. And then Laplace took it even further. Why do we even need a God to create it? Maybe these material forces are as ultimate as it gets. There's maybe or he didn't believe there was any God behind them. All right, well, that was the background going into the 1800s, the 19th century. And still at this time, and pretty much through the 19th century, we didn't even have the term physics. As Olson notes, developments in that century were referred to as developments in natural philosophy. And natural philosophy from ancient Greek times was referred to really all of what we'd call the natural sciences now, but certainly in that context of the 1800s, when you had biology, geology kind of going off into their own separate domains, natural philosophy that focused on the most basic forces or elements of the world. The natural philosophy was kind of reserved for that, and eventually we started to call it physics. So what happened in the 19th century? Well, there were some developments that got away from this very mechanistic, very localized understanding of space and time, these absolutes in which everything is specifically located. And in some ways, we were starting to get back to more organistic understandings of the universe that tended to prevail through Western history until the Enlightenment. And so folks, especially Maxwell, learned all kinds of things about electricity and magnetism, electromagnetism, and they learned and developed equations that told us about the force fields that are involved with electricity and magnetism. So you got these, more rather invisible kind of forces that are real, but not localized in the way, say, a billiard ball is. So that was an important development, and then led to new discoveries in the early 20th century. So one of those things is relativity theory, that was mainly discovered by Albert Einstein. We've talked about how his insight into this was not a matter of just kind of looking at scientific evidence and mathematics and experiments and that kind of thing up to that point. But no, it involved a special kind of intuition, a new paradigm. And he tells about a vision. A vision. Sounds a little religious. A vision he had that he said involved something very corpuscular that enabled him to come up with the insights of special relativity. And that its basic assumption that there's only one absolute. It's not space or time. It's the speed of light. And the speed of light is that one constant. 186,000 miles per second, that's rounding it off, something like that, if I remember correctly. And that's constant for all observers, whatever your frame of reference. But space and time and how those are experienced, how those are measured, is relative to your reference frame. Now, special relativity basically just looks at the space and time in relation to how fast an observer is moving relative to the speed of light, relative to some other object that's not moving that fast according to the person who's going closer to the speed of light. Now, as we've already said, in our everyday world, Newton's laws of motion and force and energy and all that work perfectly well because we're nowhere near the speed of light in our own motions on Earth. But at speeds getting closer to the speed of light, there are some huge differences in how time passes. So one of the manifestations of that is the so-called twins paradox, where you have two twins on Earth, say they're 20 years old, and the one twin stays on Earth, the home body. The other, the space traveler, goes off pretty close to the speed of light, and probably, I'm doubtful that that would take huge amounts of energy. I'm doubtful that it's ever going to happen, that we're going to get that close to the speed of light. Sorry, Star Wars and Star Trek and that kind of thing. But anyway, in this thought experiment, the one brother is going near the speed of light and then comes back near the speed of light, and so he gets back and he's, say, 40 years old, and his twin brother is now 80 years old. Yes, that could theoretically happen if that traveling brother got close enough to the speed of light. So what's events that are simultaneous from one perspective may not be simultaneous from another perspective. And that would be very noticeable if an observer is moving at speeds that are getting closer to the speed of light than we have in our everyday world. Now, you can do some of these experiments to prove this, thought experiments with flashes of light that are equidistant to one observer, and a train is moving, and then they're not they're simultaneous for one observer, but the other observer who's moving, they're not simultaneous. So when you use light itself to conduct a thought experiment, you can see these effects even here on Earth, not in terms of our movement, but in terms of the movement of light. We could imagine in another thought experiment that someone is flying near the Earth at very high speed, kind of relativistic kind of speed, fairly near the speed of light, and there's an explosion at one point on Earth and an explosion at another point on Earth, and from the perspective of the observer on Earth, they're simultaneous. From the perspective of this space traveler, this very fast traveler, they would not be quite simultaneous, especially, I guess, the further apart they were. But there are limitations. So time is not, the passage of time is not absolutely relative. That is, if, say, explosion A happens before explosion B, say now to the Earth observer, we'll say that the one happens before, but for the space traveler, the way she is going, we'll say they are simultaneous, but it will never happen that the event that was first on Earth will actually happen after the event that was second from the Earth frame of reference. So, frames of reference can vary tremendously, and again, some things could be simultaneous from one frame of reference and definitely not from another perspective, but you can't actually reverse if any one perspective has event A happening first and event B happening second, it's never going to happen that event B happens first and event A happens second from any perspective. All right, so that's something about special relativity. And you might note that there's 4 dimensions. So we talk about space-time given relativity theory. 3 dimensions of space and then the 4th dimension of time, which are interrelated. Now, general relativity is the theory that gets more directly into space, and it gives an explanation for gravity that is rather different from the assumptions of earlier times, going back to Newton, where gravity did kind of seem to be this maybe one thing that wasn't so localized and maybe a little less mechanistic than everything else. But the truth is that space is not an absolute. Space is curved relative to the mass of objects. So gravity means that space is curved. The geometry that pertains to our universe is non-Euclidean. It's not, straight, 3 dimensions where everything is linear. No, things are curved, not straight. The first major experiment that proved the curvature of space was when some electromagnetic energy was shot past the sun, and because of the sun's huge mass, those photons, waves of electromagnetic radiation curved around the sun. So even those photons without mass were affected by the curvature of space. Okay, so much for relativity theory. Fascinating stuff. But let's get to quantum theory, quantum mechanics, quantum physics. What does the very term quantum or quanta mean? Quantum means one, quanta means many, quantum. Basically, it means that things only come in certain sizes, certain amounts. Now, if we talked about how, from Newtonian mechanics, and we can say for our everyday world, our everyday macro world, the larger world, that our movements are continuous. I can be here, 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 and if we're measuring it by inches, here's 2 inches, here's 1.37 inches, and it's all continuous. But if I were able to only move, or my finger only moved in a quantum fashion, it would only be able to be here at inch 1, and then if it moved, it would not go between 1 and 2, it would just next pop up at location 2, 2 inches, and location 3. So everything is in discrete, particular packages of a certain amount of, say, energy. So we can talk about quanta as wave packets. And what we find out actually at the subatomic level and the level of electromagnetic radiation is that things involve basic particles exhibit both wave-like behavior and particle-like behavior. Here I might say a word about atoms, which literally means cannot be divided. Well, they were basically discovered by Dalton in the early 1800s, but by the early 1900s, it was proven that there are more basic particles that make up an atom. And, since in more recent times we realize that protons and neutrons are made up of even more basic particles, mesons, different types of mesons. But all these subatomic particles behave in quantum mechanical ways, quantum physical ways. And that has a number of implications. Schrödinger was one of the thinkers, the great thinkers of quantum mechanics, and you might have heard about his cat box, where we have in the physical world, the quantum world, we have wave equations, and there are certain probabilities about what will happen with light or subatomic particles. And so things are uncertain in a wave or in a photon, and within the wave there's no one particular location where the energy is localized. And so there's only probabilities until something happens, until there's, from our perspective, a measurement, but it could be any kind of interaction, right? So it's kind of like there's a cloud or a field of possibilities with certain probabilities on the quantum level. and that, again, Heisenberg uncertainty principle. And those only become definite when there's a measurement or some other kind of interaction with another particle or electromagnetic energy. And so physicists talk about the wave collapsing when something becomes determinate. So things are, at least as far as we know, indeterminate. And indeterminate means not predetermined by the past conditions. And remember, that mechanistic view of the universe said, given the positions of everything, initial positions, and the laws of physics, you'd be able to determine everything if you were smart enough, right? But no, at least as far as we know, that's not the case in the quantum world. There is, at least for all appearances, indeterminacy, and things become determinate only when there's an interaction. And so, well, the cat in the box thing as well, there's a cat in the box and we don't know whether the cat is dead or alive, and in fact, the cat isn't either. If this were a quantum cat, the cat is, a possibility, a possible cat, an either alive possible cat or dead possible cat. And only when you open the door, the box, and interact with the cat, then you know whether it's dead or alive. Okay, got all that? It's funky. And some other things about this uncertainty and how things become determinate when interacted with is you have some inverse relationships. That is, you can't measure both the position and the momentum or energy of something on the quantum level. If you measure position, you don't know the precise momentum, and vice versa. Also, there's there's an inverse kind of relationship in relation to energy or time when it comes to radioactivity. Now, there is, not pure chance when something that is radioactive, a bunch of radioactive material, as to how much it will decay over a given period of time. No, that the overall the decay is determined. That is, if it has a half-life of, say, 1,000,000 years, half of those, say, a particular type of uranium atom will decay into something else in 1,000,000 years. But as to which, here we'll pick out atom Z in this uranium sample, and we can only say, well, this is the probability that it will decay in the next 5 minutes. This is the probability it'll decay in 1,000,000 years. And so we don't know at all which of these will decay when. Now, Barber's, if you're only going to read one, and you should read all our readings, but if you're only going to read one, or the first one to read would be Barber, because remember, he has the different models that are in the background for our whole course of possible relationships between religion and science, right? Conflict, independence, dialogue, and interaction. But he gets into different ways to interpret the apparent indeterminacy. Einstein couldn't stand indeterminacy. He didn't believe in a personal God. He was Jewish background. He believed in a pantheistic God, but the universe is totally rational, he believed, and so he couldn't believe that these quantum events were indeterministic. He believed there was their determinism that we just don't know. And we still don't have any clue or any evidence at all that there is any determinism. But some of this goes with the independence model. An instrumentalist view says, okay, who cares what the ultimate status of things are ultimately indeterminate, or whether there's some determinism going on we don't know about. An instrumentalist is concerned with just, say, harnessing quantum mechanics to benefit humanity, to benefit hopefully maybe some other creatures on Earth as well. Then there's epistemologist indeterminists who would say that, well, we don't know whether ultimately, ontologically, metaphysically, the way things really are in themselves, independent of us. Of course, they're not totally independent of us because, when we measure, they become determinate. But anyway, we don't know whether things are ultimately determinate or indeterminate. But as far as we know, as far as our knowledge can go, they're indeterminate for our knowledge. And then really the majority view in physics is that there really is ontological uncertainty. To use the analogy of that cat again, that cat, if it's a quantum cat, is neither dead nor alive, just possibly dead, possibly alive, until something happens, there's some kind of interaction that determines what will become determinate and when it will become determinate, how it will become determinate. I hope this is blowing your mind.